Right, Bismillahirrahmanirrahim. So, last time, before the lab, we saw a problem which was that if you're going to have multiple IP addresses, they're going to be unique globally, the public IP addresses. If they're going to be unique globally, you are going to eventually run out of IP addresses. And there were several reasons for that. So primarily, the reason is that, so the primary reason of running out of IP addresses is that there are just too many devices in the world. Okay, so yes, there are issues such as organizations buying a lot of IP addresses, very large blocks and all of that, but that's not all that important. What's most important issue is that there are just too many devices, especially when you have IoT, which essentially means very small devices also connect to the internet. Okay, so this is this was foreseen by people a long while ago. So I can tell you that I took my networks course back in like 2003 or 2004, that like 20 years back, and this issue was discussed even then, right? So the solution that we're seeing, yes, so it has been foreseen, this problem has been foreseen since that time. So people knew, so we actually studied the problem and we knew that there is a thing which has been proposed at that time. It had already been proposed that this is the solution. Okay, so we have to see what the solution is and what to do with it. So the idea is that if you have just 34 bits, if you have just 32 bits, and associated with these 32 bits are several issues. So once you have that, there is a fixed number of IP addresses that you can have. Okay, so if you have many different devices connecting to the internet, then you're eventually going to run out of this. So they came up with this solution a long while ago that we should have another version of IP. So this is IP stands for Internet Protocol, right? So Internet Protocol. Initially, it was just the Internet Protocol. Okay, what is the Internet Protocol? It's a protocol which works on the internet layer and it provides IP addresses or addresses which can work on layer 3. Okay, so when this was realized that this is an issue, they called this the Internet Protocol version 4 and they proposed another version which is version 6. Now, I'm not sure where version 5 went, but maybe it was a proposal which had issues, so they scrapped it somewhere. I don't know. Anyway, the point is that this thing is called IP version 6. And the major change, which basically leads to other changes, is that IP addresses are no longer going to be 32 bits, they are going to be 128 bits. Okay, so as you can see, if you have 32 bits and you increase it to 33 bits, you essentially double the amount of IP addresses. Agreed? So if you go from 32 bits to 33 bits, you double it. Then if you go from 33 to 34, you double it again. 34 to 35, you double it again. So every new bit which is introduced basically doubles the amount of addresses that you possibly have. So now we are increasing approximately like 90 something, I don't know. So 90 something bits are being added. So the whole address is now 128 bits. So the amount or the number of possible IP addresses in IP version 6 is huge. Okay, so if you calculate 2 raised to power 128, it's a huge number. Okay, so for the foreseeable future, because when they were doing this, you could have thought that why not just do it 64 bits. They said now the actual processing of the IP addresses, it's so fast, the computers are so fast that processing a 64-bit number and a 128-bit number, they're essentially identical. It doesn't take time if you want to process 128-bit numbers. Okay, it's just an ANDing operation mostly. So let's just have 128 bits because that is going to take care of it for the centuries to come. Okay, so we're done. Unless something radical changes later on, and for example, if you have like AI taking off and robots taking over the whole world, then let them take care of the IP version 8 or something. Like it's not our concern anymore. Okay, so that's the point, that they gave it such a large space so that it's a one-time solution and it's done. Why? The reason for that is that if you go from 32-bit to let's say 64-bit or 128 bits, I alluded to this earlier on as well. I gave you a hint of this. But see, the problem is now you have all the hardware which is deployed in the world and the whole world is connected with everything. Okay, so it's a whole big connected thing. And if you want to change one hardware so that it can recognize 128 bits, right, you have to change the hardware which is communicating to it as well. And then you have to change the hardware which is communicating with that, and the hardware which is communicating with that. So essentially you have to ask everybody in the world to change their hardware at the same time. So it doesn't work like that. Okay, you simply cannot do it. It's impossible. Okay. So imagine that if you ask the whole world to shut down their internet for, let's say, 1 day, it's not going to work. You cannot ask people to shut down internet. So the first time I heard of this, I was like, fine, what's the issue? I mean, shut down the internet. But we look at the internet from our perspective, which is a user's perspective. Think of this in terms of the infrastructure. So all the electricity grids, for example, they rely on the internet to provide them a lot of information. Okay. So if you shut down the internet, you essentially shut down electricity. If you shut down electricity, you shut down everything, right? Imagine if you don't have air conditioner for 1 day. It's simply not possible. Okay. But it's not just that. If you shut down then electricity, then you don't have any electricity for the like malls, right, where food is stored. So in 1 day, all of that food is going to go bad. It doesn't work. If you think about it, all the infrastructure, so you have satellites. If you lose communication with the satellites, you don't know where they are, and then it's no longer possible to identify their location. So it's a big mess. Okay, so losing electricity, if you don't know, one of the greatest threats nowadays, one of the greatest threats to civilization is not like a meteor hitting or an asteroid hitting the planet Earth. It's that you have a global blackout. A global blackout would ruin everything. Okay, so it's a huge thing. So coming back to the point over here. So coming back to the point, you cannot ask people to shut down the internet. So changing it is an issue. It's such a big issue that they actually came up with solutions of how we can go from IP version 4 to IP version 6. So see, the issue is, if you ask everybody to change from IP version 4 to IP version 6, even though the change is very small, but hardware has to be changed. So either everybody does it together or people do it slowly. If everybody does it together, it's not feasible. But if people do it slowly, for example, if I run an organization and you tell me that we're starting with you, first you go and buy the router which is 128-bit address capable. Okay, so just me. Let's say I run a very large organization. Okay, again Amazon, I wish. But let's say I have a very large organization and the standard people tell me that you're supposed to go and change the routers to these new routers. Okay, I don't want to do it. Why me? Ask somebody else to do it. Okay, so because it's an investment. Why should I put in the money when my competitor isn't doing it? Okay, so it's very difficult to get people to actually change over. So you cannot change everybody together, and if you ask somebody to change, they're not going to change. Why invest in some? I mean, the internet is working for me. Why should I change? It's not going to work after 20 years. I don't care. See, so it's not a solution. So they have to come up with a technical solution, and they came up with 3 solutions. Okay, so that is this point over here. The first thing is dual stacking. So what that means is a device will run both IP version 4 and IP version 6 protocols simultaneously. This is the easiest solution. So let's say 20 years back, starting in, let's say 2002, all the routers which are manufactured, they are capable of doing everything that IP version 4 was doing, and they're also capable of doing everything that IP version 6 is doing. Okay? But you can again imagine that it's going to cost money. If you had a device which was doing this much, now you're asking it to do this much. Both this and this. So they're equal, but now there are 2 things that it has to do. So obviously the price of the router is going to go up. So it's an economics issue. People just don't want to do it. Okay? But slowly they made improvements, and slowly this is probably the most common thing that has come up with. So this is not just like hardware, routers and switches and all of that, not switches, routers, but it's also operating systems. But remember, it's the operating system which has to initiate everything, right? So it's the operating system which talks to the hardware and everything. So the operating systems for the past 20 years have had the capability of specifying an IP version 6 address. Because it's software, we can change it very easily. Okay, so there is still, and there has been for a long while, the capability of assigning an IP version 6 address to all your Windows hardware. It's possible. It's very easy, in fact. Okay. So the capability is there. It's just that people don't use it. Why don't they use it? Because the other person is not using it. Okay. You understand? So why is nobody doing it? Because the other person is not doing it. Why are they not doing it? Because I'm not doing it. And why are they not doing it? Because we are not doing it. So it's very slow process. Okay. Even though the solution itself seems very easy, just change the 32-bit to 128-bit, but it takes time. Okay. It has taken, in fact, a long while. And even now, all the communication which is going on in local area networks, almost everywhere, it's still on IP version 4. Okay. So if you're doing IP version 4 over here, and you're saying that globally it has to be IP version 6, then how do you do this? We have other alternatives as well. So one is called tunneling. Tunneling is the method of transporting an IP version 6 packet over an IP version 4 network. What does that mean? Your infrastructure is still IP version 4, but what you do is you remember that in our message that we encapsulated, so you have the Ethernet information, the source and destination MAC addresses, and then you have some place where you put the data. It just said data. Okay. So in that data you can put anything. So what tunneling does is creates an IP version 6 packet and puts it in that data portion. Okay. So your routing and everything is still happening using IP version 4, but if a device wants to do IP version 6 addressing, it can simply take that information out and then use that for further routing. So the way this is going to work is, this is a local area network which works on IP version 4. Okay. If you want to send out an IP version 6 packet, you take the IP version 6 packet, you construct it as normal, and then you put it inside the data portion of an IP version 4 packet. Make sense? Okay. Now it's there. So the packet goes out using, so it does all its routing over here, then it goes out to a network which is capable of doing IP version 6 addressing. Okay. So what is the first device over there is going to do? It's going to read the IP version 6 packet and it's going to get rid of the IP version 4 packet. So all of this routing over here is going to happen using IP version 6. Okay. And the final device which is going to now talk to the IP version 4 network, which is another local network over here, which is working on IP version 4, the final device over here is going to again do the encapsulation, the tunneling. It's going to take that and it's going to put it inside of an IP version 4 packet and then send it out over here. So over here, you change the IP version 4 packet to 6, and over here you change the IP version 6 packet to 4. So this is called tunneling. It's called tunneling because you create a tunnel and you put stuff inside of it. Okay. So why are we doing this? Because people cannot change to IP version 6 immediately. We are trying to create solutions which kind of make both of them work together. Why? Yes. Even nowadays, all the new devices still have IP version 4 capabilities.
But the new devices?
Even the devices which are manufactured today, they still have IP version 4 capabilities. Because again, the thing is, IP version 6, they have to support. IP version 4, what if we want to deploy it on this network and we want to use IP version 4 over here? So like I said, in local area networks, in small environments, IP version 4 is still very common. And you'll see why in just a minute. Okay, you'll see in just a minute why we don't want to do IP version 6 directly. Okay, it will take like 2 seconds to explain it to you. Okay, so the third method is translation. As the name suggests, a packet comes in, it has IP version 4 addressing, and the rest of the network over here is IP version 6. So I'm going to just change the IP version 4 address to another address which is IP version 6. Okay, just as a router can change the MAC addresses, it can also change the layer 3 addresses. Okay, so we have new protocols which can actually look at an IP version 4 address and basically change it, translate it to IP version 6. So what's the difference between tunneling and translation? In tunneling, there is an actual IP version 4 packet and it holds the IP version 6 packet in its data portion. Translation, essentially, you have just one packet. Initially, it was IP version 4 packet. When you send it onwards to someplace else, you're going to actually change the address from IP version 4 to IP version 6. So that is what translation means. Is clear?
Doctor,
yes.
Tunneling, if I have IP version 6, I put IP version 4 inside IP.
It's confusing if you try to think of this like this in text. Think of it this way. Your infrastructure supports IP version 4.
What if opposite way?
Yes, but that's not generally. If you have IP version 6, then you can just use that. If there is an infrastructure which has IP version 6, then you don't want to put IP version 4 inside of that. It's possible. Maybe in some situations it's done. But the issue is that you want to do IP version 4 routing, but you also want to send IP version 6 information. So you take the IP version 6 information, treat it like any other information, put it inside IP version 4. So the way to remember this is your infrastructure, the legacy infrastructure, the old infrastructure is capable of doing IP version 4 routing. So that's the addressing that you're using. What is it carrying? It's carrying the information that these people do not know, which is IP version 6. Okay? Clear? Make sense? Okay. All right. So you have these three things. So all three of these are used in different situations. Okay. So this is not very important. You can read this. Okay. So here's the reason of why we don't do IP version. People don't want to do IP version 6 because an IP version 6 address looks like this. Right. So this is what an IP version 6 address looks like. So they are 128 bits in length. Okay, they are written in hexadecimal because if you write 128 bits in binary or decimal, it's going to be even larger a number. It's very difficult to manage this. 128 bits is a huge number of bits. Okay, if you just try and write it down once, it's very difficult. But the point is we don't have to. I mean, it's the same operation, right? The ANDing and everything that we've studied in IP version 4, they're the same operations. In 32 bits, we can actually write them down and look at them. In 128 bits, it's just a mess. So we convert them into hexadecimal, the operations are exactly the same. Okay. So IP version 6 addresses are not case sensitive because you are now in hexadecimal. Now you have to worry about cases. So for example, hexadecimal can be FA80. It can also be FA80. So are these two the same or different? So they're the same. Case insensitive. Okay. You can write them either way. Generally, they're written in lowercase. For some reason, I don't know. But generally, they're written in lowercase. Okay, maybe it's written somewhere over here. The preferred format for writing an IP version 6 address is this thing over here, where each X consists of 4 hexadecimal values. So 1, 2, 3, 4, 5, 6, 7, 8. 8 fours are 32. So 32 hexadecimal. And each hexadecimal character corresponds to 4. 32 fours are 128. So that's how it becomes 128 bits. Okay, so you kind of have to get used to it. Okay, now you can no longer pronounce. So up until now, we've been very easily saying 192.168.0.2. Okay, it's very easy to say it after a little while, of course. But this thing, you cannot say it. It's just horrible. Okay, it seems like a very silly point. Excuse me, but that's one of the reasons why people don't want to move to this, because it's messy. I mean, you have to do this. If you ask the lab engineer over here to assign these IP addresses, it's a mess. People don't want to do it. Okay, so it's a silly point. It's not a technical issue, but it's still there. Okay, that's why mostly in local area networks, all the communication is still using IP version 4 because it's a lot easier to manage for us humans.
Let's say the new devices that are coming, they are not using IP version 4.
They use both.
How?
So the capability is there. If you bring a new router, for example, over here and you want to put it over here in your LAN, the router is capable of doing both IP version 6 and IP version 4. So if you can... Right. So public IP version 4 addresses are not available. Right? Yeah. Private are just, they're not globally unique. So you can have a 192.168.0.1 here and there and there and there. So the private portion, people are still using it. And because when you create a routing device, it's a lot cheaper nowadays. The hardware has become cheap enough that adding the IP version 4 capability is not that, it doesn't lead to the cost increasing that much. Okay, so it doesn't affect the cost that much. So you have both. You can. Okay, so all the modern devices have both. Maybe in like a long while after it, people get used to it. Maybe IP version 6 will be the only one, but it doesn't look like that because for these, the human ease is not going to go away. This thing is never going to be easy for any humans. Okay, so people are generally going to just stick with IP version 4 for small enough environments. Okay, imagine that when we started, instead of saying that give it the IP address 192.168.0.1, I said this. It's the same idea. It's just a number, but it's such a large number that it becomes very difficult to like think about these things. Okay, so it's a human limitation. Anyway, in IP version 6, a hextet, so this thing is called a hextet, right? So is an unofficial term used to refer to segment of 16 bits. So what that means is 4444. So this thing is a hextet, hex coming from 16, right? So okay, so this one thing is now called a hextet. In IP version 4, the octets were separated using decimal points, right? Here the hextets are separated using colons, okay? And the reason for that is just by looking at it, you can see that it's an IP version 6 address, not an IP version 4 address. As soon as you see a colon, it's an IP version 6 address, okay? So anyway, we'll come to examples of why this matters in a minute. Okay, so this is the format, example format. So this whole thing, it's a number, 128-bit number. We have just put separators in the middle so that it's easy for us to see. Otherwise, if it was just 20010 db 000011, it would become very even. It would become even uglier. It's still very bad now. So everybody agree that this is a horrible way to write stuff. Okay. So one thing that you can see over here is that there are many hextets over here which start with all zeros. So this is a 0. These are all zeros. So this is a 00, and this is a 0, and this is a 0. So a lot of zeros. What the number of characters? Yes, but each one is a hexadecimal. If you translate it into binary, it becomes 4. Each character becomes 4. So 4 into 32 is 128. Okay, all right. So if you see over here, say this 0200 and all of these other ones, they have a lot of zeros in the beginning. So there are two rules which can allow you to reduce the size of this whole thing. Okay, it's going to be the same number, but we will be writing a lot less. You understand the objective of the next slide? In the next slide and next two slides, we are going to be writing the same number, except we'll come up with rules which can unambiguously, without a chance of mistake, allow us to write fewer numbers and still get the same IP address. Okay, so the first rule is you get rid of all the leading zeros. So leading means which are on the left. They lead and then the numbers follow. So leading zeros. Not the trailing zeros. Trailing zeros means which come at the end. According to English, leading is on the left and trailing is on the right. So the first rule is you can get rid of all the leading zeros. Why? Because for example, I write 2001 colon db8 colon and then something over here. Okay, you can immediately see over here that these are just 3 characters, and that means that each hextet has to be 4 characters, and that makes it very clear that 0 is missing over here. Okay, there is no other chance. Why? Because we said we are going to get rid of only leading zeros. It cannot be db80 because we know that we will only get rid of leading zeros. Okay, so that's the first thing. So you can get rid of this 0, you can get rid of all of these, you can get rid of these zeros, and you can get rid of these, and you can get rid of these. So you only have 2001, db8, a3, abcd, 1, 2, 3, 4. Okay, I said it. Yeah, we're coming to that. Okay, make sense? Okay. So rule 1, omit leading zeros. It's very important that you remember the word leading, only leading zeros, not the trailing zeros, because then if it's db8, you don't know whether it was 0 db8 or db8 0. You don't know. It creates a confusion. So you can't have that. You can only get rid of leading zeros. So 01AB can be written as this can be written as this can be written as this, and this can be written as this. It doesn't matter if you have 1, 2 or 3 leading zeros. You can get rid of all of them. Okay, it's still unambiguous. This is fine. Not 2 trailing zeros. If you also allow the removal of trailing zeros, then it's a mess. You cannot have that. Okay. So for example, if you have 9F00, you cannot write it as 9F because those zeros are trailing zeros, not leading zeros. 009F can be written as 9F. Okay, makes sense? Because if you allow this and you see a 9F, you will not know which one it is. Was it 009F or 9F00? So we simply get rid of that possibility. So now we have and unambiguous, this is called a deconstruction. So you can go back to the original. Okay, this is clear? Okay, good. The second rule, double colon. So this rule is very straightforward, but it's confusing when you first start looking at it. So make sure that you pay attention. So a double colon can replace any single contiguous string of one or more 16-bit hexadecimal consisting of all 0. What that means is, if you have all zeros, you can just get rid of it. Okay? If you have all 4 zeros, you can get rid of it. Also, if you have 8 zeros, you can get rid of those as well. Not 7. Like either 4, 8 or 16 or 34, whatever. Okay, I'll give you an example. Okay. So for example, this thing over here. So first what did we do? We got rid of the leading zeros to get this. Okay, so not this one. So it was originally 2001 0db8 CAFE 0001 0000 0000 0000 That is what it was. We got rid of all the leading zeros. We left with this. Okay. Now, if you have all zeros over here, you can get rid of them. And this can be written as this thing, which is this portion over here. Then all the zeros are replaced with a double colon and then whatever comes after it. Okay. So if you have all zeros, all zeros, all zeros, all zeros, all zeros, you can get rid of all of them, but they have to be contiguous, attached to each other. They cannot have a space in the middle. We'll see why in just a minute. Okay. You can just get rid of them and put a double colon. If you look at this, for example, if you look at the address 9F::2. Now this is a perfectly valid IPv6 address. Let's convert this into what it originally was. Okay. So you remember that IPv6 address has to be 128 bits. Okay. It's going to have 1, 2, 3, 4, 5, 6, 7, 8. It's going to have 8 hexadecimal. Okay. So this 9F will turn to 009F. Sorry. And at the end, you're going to have 0002. So, clear? And everything in the middle is a 0. So now you write 0000, 0000, 0000, until this whole thing becomes how many? 1, 2, 3, 4, 5, 6, 7, 8. So 2 of these, 1, 2, 3, 4, 0000, 0000. So that is the IPv6 address, which we can write as that as well. As you can see, it's possible, not always, but in certain cases, it's possible to shrink the whole 32 hexadecimals into a much smaller representation. And you can create it automatically very easily if you understand the rules. Okay. So this thing, for example, over here, 2001 db8, you immediately see that a leading 0 is missing over here. So this is going to turn into 0 db8. Then there is a 0 over here. Then we have 1111, and then we have 2 colons over here, and then we have the 200 over here. Okay. So this is going to this 200. Let's get rid of this whole thing. This whole thing is this thing, their equivalent. Okay. So this 200 becomes 0200. This is the same. This becomes 0 db8. This 0 becomes 0000. This 1111 is as it is, and this colon becomes whatever is left. Okay. So you have 1, 2, 3, 4, and 5. They have to be 8. So you have 3 zeros in the middle. Is clear? Okay. Okay. Why did we not just get rid of this 0 as well? It's a 0. So why not just get rid of it? So you can, yes. So you can only have one double colon. Why? Let's say we had 2. Let's say we got rid of this as well. Okay. So let's say this was 2001 colon db8 colon. So this is a colon 1111 colon 200. So this you can convert to 0200. Fine. This you can convert to 0 db8. Fine. But now these two are left. And there are 1, 2, 3, and 4. How many hexadecimal left? 4. How many go here and how many go there? We don't know. Make sense? Right? So generally, when we get rid of the zeros and replace them with double colons, we want to do it with the largest number possible. Okay? But you can only have one double colon in one representation. This is called a compressed notation. So you can only have one double colon, not two. So because this one was already taken by these three, then that 0 we could not get rid of. So we just put it in. We could get rid of the 3 leading zeros, that's fine, because that's unambiguous still. But we could not get rid of the 0. That 0 had to remain over here. Makes sense? So that is why it says can replace any single contiguous string of one or more 16-bit hextexts of all zeros. So if you understand it, then this sentence makes sense. Okay? It has to be one replacement. You cannot do two replacements. It has to be contiguous. They have to be attached. Otherwise, we would not know where the zeros are. One or more 16-bit hextexts. So the whole hextet has to be a 0. Otherwise, again, we will not be sure. And they all have to be zeros. Okay? Make sense? So 2 rules only. You can get rid of the leading zeros, and you can remove single contiguous all 0 hextexts and replace them with a colon. You can come up with your own wording for the rule. Okay? This is the official wording. You can come up with your own wording, just anything that helps you understand. Is this clear?
Yes.
Okay, good. So this is just to make IP version 6 addresses a little bit more manageable for us. Okay, all right. Other than that, the rules are pretty much the same. For example, in IP version 4, we had the network portion and the host portion. Same thing over here. We're going to have the network portion, and the host portion, we're just going to call it the interface. Instead of host, we're going to call it the interface. It's the same idea. Okay. Why? Because hosts were typically PCs. Now you can have like watches and shoes and whatnot. So we call them interfaces and not hosts. Just a change of terminology. Okay. So same idea. You use /64, which means 64 bits are going to be for the network portion and the rest of the 64 bit for the interface ID. It's called an interface ID instead of the host portion. Okay. Everything else remains the same. It's the same ANDing process. If you write /64, now writing a whole subnet mask of 128 bits is going to be a mess. So we just use the prefix notation or the slash notation. Okay. All right. Same idea. Exactly same as IP version 4. There are quite a few special IP version 6 addresses. We don't want to go into all of them. I'm just going to show you 2 of these important ones. So this guy over here, now you see ::1. This is a perfectly valid IP version 6 address. Why? Because we know the rules. This 1 becomes 0001 and the 2 colons become all the rest of the zeros. So it's 7 hextexts of zeros and then 0001. Okay, makes sense? And from that, all 128 bits are for the host portion. What essentially that means is this is the equivalent to 127.0.0.1 in IP version 4, which was the loopback address. Okay, so the loopback address in IP version 6 is ::1, like globally understood. Just as 127.0.0.1 is globally understood as the loopback address in IP version 4. Okay. Similarly, we had something called link local address in IP version 4. That over here is : And what is : All zeros. Okay. Make sense? All right. All other addresses, well, it's not technically accurate because I got rid of some other addresses. So there are some other special addresses as well. They're not very important for us. But everything else is going to be a global unicast address. Unicast means it's going to be assigned to a particular device. Okay? Make sense? Okay. The routing, we did public and private addresses in IP version 4. So they had certain ranges. It's the same idea over here, but now it's a lot cleaner because you have a lot of bits to work with. Okay? There we had to define ranges because we had just 32 bits. So we had to define this portion over here is public and this portion over here is private. Now it's very easy. We say that all of these portions over here, these 48 bits in the beginning, right? You look at those. If they are in a particular range, then this is a public address. If they are not in that range, then it's a private address. I'll show you the range in just a minute. You just look at the first 48 bits. If they fall in a particular range, it's a public address. Otherwise, it's a private address. Okay. Then you have this portion over here, which is going to be the subnet ID. So again, a few bits for the subnets. Now it's very clean, right? Because you have a lot of bits to work with. And then you have the interface ID over here. Here, the subnet ID is fixed to 16 bits. It's a huge number. So you can have a very large number of subnets. And the interface ID is 64 bit as well. You can have quite a few different interface IDs as well. Okay. So you kind of have to remember these, right? So because it's important that you know that 48 bits are for the global and then 16 bits for this and 64. I don't remember because I don't have to sit in the exam. Maybe I will, but anyway, you have to, okay? So this is just a description of that. So global routing prefix is the prefix or network portion of the address that is assigned by the provider. So remember, the public IP addresses have to be assigned to you by somebody else. So this portion is going to be assigned to you by somebody else, okay? Subnet ID is the area which basically identifies the subnets, just as it did in the IP version 4. And interface ID is equivalent to the host portion of IP version 4. Again, same ideas. If you understand IP version 4, so somebody asked me, why are we doing IP version 4 if you're going to go to IP version 6 anyway? IP version 4 is a lot easy to understand. Once you understand it over there in smaller number of bits, it's the same idea over here, okay? It's just that the number of bits is now very large. Is this clear? Okay. So you have 48 bits of global routing prefix, 16 bits over here, and 64 bits for the ID. So your globally unique assigned address, so GUAs. So these things are given to you by certain by organization. So I got rid of those, but for example, this 2001 over here, this number 2001, this is one of those things. So IP version 6 addresses, public addresses are in such large number that initially they are only assigning 2001 numbers starting with 2001, and the whole world, for the moment, it's sufficient for the whole world, okay? So numbers starting from 001, those are currently public IP version 6 addresses. Just 2001, they're sufficient for the whole world at the moment, okay? Later on, they may change this to 2002 if more people come in and they have to assign it though. So it's a huge number. Why? Because the first thing is going to be 2001, then you have quite a lot of different possibilities over here after that. So those possibilities are large. So see, this is 48 bits. This thing over here is 4444, 16 bits. So the global portion is 16 bits over here, which is 2001 fixed. And this thing over here, you have 32 more bits, which can be. So the whole possibility of IP version 4, everything that you had up until now, that goes in just 2001. You can have all of those possibilities over here. Agreed? IP version 4, all possible IP version 4 addresses were 32 bits. They can go in just this portion. So if whatever IP version 4 was assigned to me, it can be assigned to me again. Okay. A very good example of this is, I don't know whether you've seen this happen in your lifetime. Probably not, because so I have been lucky enough to have started working in tech when it was evolving. So I've seen all of these hurdles that people have faced. So there has been it's a very stupid thing, but I actually went through it, so it's very easy for me to understand this. So when I started, the phone numbers, the landline phone numbers, they used to be like 6 characters. Okay, so 6 characters, 6 digits. Okay, so whoever came up with the telephone numbering system, they thought 6 characters was fine. Okay, because who's going to need a phone anyway? I mean, why do you need a phone, right? When I was a kid, why would you need a phone? So people started getting landlines. So eventually they ran out of numbers. So they said, okay, what do we do now? So everybody who has a phone number right now, we change their phone number to 6 and then their old phone number. Okay? 6 and then their old phone number. What good does that do? It's the same number. But now I can have 7 and as many new numbers now. And 8 and as many new numbers now. And 0 and 2 and 4 and 3. So all of these possibilities. So I have essentially multiplied the possible number of addresses by 10. Okay. So over here, all the IP addresses, public IP addresses, have essentially been multiplied by 2, and then again by 2, and then again by 2, and then again by 2. So 2 raised to the power 16 times they have been multiplied. So 2 raised to the 16 is a huge number. Okay. Understood? Okay. So it's like 65,000 something. So you've taken the capacity of the world currently and multiplied that capacity by 65,000. Okay. Make sense? The point that you have to understand is 16 bits are assigned to globally unique identifiers. Some technical organization comes up with this, probably Internet Engineering Task Force, I don't know, I don't care. But some standard organization says that this number, we're going to use this. Okay, and later on when we run out of these, we are going to change the 2001 to, let's say, 2002 and start assigning new numbers now. Make sense? Okay. So that's the whole idea here. So you have these three portions. Finally, you can also have subnetting in IP version 6. So for example, if you have this global address, okay, and you want to create a subnet ID, you assign 4 bits to the subnet. So you can have subnets. So these are 4 bits for the subnet, which means 4 hex characters for the subnet, which means 16 bits. Yes.
The previous,
Yes.
with 2001.
Currently, yes. It can change later.
Yeah,
Later they can change, right? So see, somebody has to assign you a public IP address. So right now they are assigning these IP addresses. When they run out of these, they're going to change this to something else. Okay, but now it's very easy to change it, because instead of saying you have 2001 blah 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 blah, all they have to say is you have 2002 blah 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 blah. Okay, so the infrastructure doesn't have to change now. Okay, because we already have the capacity of 48 bits. Okay, all right. So if you want to do subnetting, idea is exactly the same. You use some portion of the interface ID or the host ID for the subnets. So an example over here, you use 4 of these. So what that is going to mean is you're going to have 16 bits for the subnets. Okay, so you can have 65,000 subnets over here. Same idea as before. You assign a certain number of bits for the subnetwork. Okay, exactly the same as IP version 4. No change. Any questions? So that's for now, that's all you have to understand about IP version 6. In labs, we're still going to be doing IP version 4, because as you can see, the difference, it doesn't make a difference. All you have to do is now go ahead and assign an IP version 6 address to your devices, and you're done.
In next lab, we will do the IPv6.
No. So this is just in the slides. We won't actually do it. I'll see if I can do an optional lab with IP version 6. I don't want to do that because if I start typing this stuff, it's going to be problematic. But Packet Tracer is perfectly capable of doing IP version 6. So there is no problem at all. It's just that you have to assign the IP version 6 addresses, and then you have to think about it, and it's a lot of calculations.
We can use the DHCP server.
Yes, DHCP version 6 is available, right? So there is a thing called DHCPv6, which assigns IP version 6 addresses. Exactly the same. Okay? Any other questions? Bismillahirrahmanirrahim. In the previous lab, we took a look at multiple router configuration, and we connected 3 routers with each other. So this router to this router and this router to this router, and we gave them static routes. What that means is that in this router, we told it explicitly that if you want to send some information to 192.168.2 network, you are going to send it over this wire to this particular interface. Okay, so we gave it specific instructions. So the problem with that is that if you have a wire connected from this guy to this guy, and then from this guy to this guy, okay, so let's go ahead and do this and then see what the problem is. So as before, we're going to go overhead, take this WIC2T, insert this over here, turn the router back on, close this, go over here, turn the router off, insert this, turn it back on. So this is what we did in the previous lab. So if you're not sure, please go ahead and look at that. So we are going to insert this over here, turn it back on, go ahead and close this, and we are going to fast forward until this is booted properly. Okay, so let's also go ahead and connect the wires. So this guy, serial 010 to this guy over here. Similarly, this to the first interface here. Okay, now the situation is that we told it to go on this route. Okay, but it's also possible that we have a router over here which is connected directly over to this router. Okay, so because these routers have the possibility of connecting to multiple things, it's generally the case that this is not like a sequential connection. Different routers can be connected to different routers, and there can even be loops in the middle. For example, we can have a wire connected to the second interface of this router over here that goes directly to this guy over here. Okay, so this is very possible. This is perfectly fine. So let's go ahead, in fact, and move this over here so that it's a little clearer.
So now you can see that we have this network over here, and this network here, and this network over here, and all three of these routers are directly connected to each other. Okay, so not all routers always have to be connected to each other, but you can have multiple routes to the same between same source and destination. So if this is the source and this is the destination, you can go from this or this. Now, which path is better depends a lot on a lot of different variables. We're not going into that right now, but what we're doing is we are first going to go ahead and set up our configuration without this multiple route and then see how this affects us. Okay, so let's go ahead and delete this for now. So this is gone. Let's go ahead and do the configuration. So let's go over here really quickly to fast Ethernet 0 and give it the IP address of 192.168.1.1. So let's go ahead and copy this. So turn it on, go ahead and close this, go over here, give this the gateway of 192.168.1.1 and give this the IP address of this. Okay, so let's go ahead and close this. Fast forward to make sure everything is working. Go over here, config, fast Ethernet 0, give this the IP address of 2.1 with the subnet mask, bring it on, go ahead and close this, PC2, config, gateway 101, turn on, go ahead and close this, router 2, sorry, config, fast Ethernet 0, give this the IP address of 3.1, bring it on, go ahead and close this guy over here. We've done this many times now, so we can do this really quickly. So settings, gateway, fast Ethernet 0, 101, and everything is fine now. So let's go ahead and run this. Fast forward, so everything is green. Okay, so we have three networks: 192.168.1.101, 192.168.2.101, and 192.168.3.101. We also need to give these interfaces their proper addresses. So let's go ahead and do that as well. So again, this is the same as last time. So this is going to be 10.0.0.2 with this guy over here. So let's go ahead and copy this, bring it on, go ahead and close this. Let's add a note. We always need notes so that we don't mess things up later on. Go over here on serial 010, give it 10.0.0.3, the subnet mask, bring it on, go ahead and close this, add a note, this guy over here. So this is 0.0.3. Let's just go ahead and make sure I did not make a mistake. 0.0.3, okay, fine. All right, so this is done. Let's also go ahead and give the addresses to the second one. So this is going to be 11.0.0.2. So let's go ahead and copy this, bring it on, add a note. So this is 11.0.0.2, and similarly this guy over here, serial 010, is going to be 11.0.0.3, and this guy over here. Let's go ahead and close this and add a note over here as well. All right, so hover over this just to make sure that everything is fine. So let's see, serial 010 is 11.0.0.3. This guy over here, serial 010, is 10.0.0.3, 11.0.0.2. So this is like a really quick view of what's going on. Okay, and this guy over here, serial 010 is 10.0.0.2. So everything is fine. Okay, good. So now what we can do is this we did in the previous lab. Let's fast forward. So now if you try to ping from this guy to this guy, you cannot. You can ping here, but you cannot ping over here. Okay, so what we want to do now is to do routing, but we don't want to do it manually. We don't want to specify next hops manually. Okay, all we are going to do is we're going to go ahead to this router and we're going to tell it that these are the networks that you're supposed to route to. Everything else it's going to take care of on its own. Okay, so let's go ahead and see what it means. Click on the router. Now in the routing, instead of static, you go ahead to routing information protocol. So this is a routing protocol which is called routing information protocol. Here, so in static you have to specify network, the mask, and the next hop. In routing information protocol, all you have to do is specify the route which you want this router to take care of. Okay, so that is going to be all of these networks over here. So let's go ahead and add these. So it's going to be 10.0.0.2. Okay, so let's go ahead and copy this. it's also going to be 11.0.0.2. So 0.0.0, I guess. Yeah. So we had to add the network. So it added the network itself. Okay. We also need the right. So these two, and we also need to add the 192.168.1.0. Let's go ahead and copy this. We also need 2.0, and we also need 3.0. Add. So what we're saying is these are all the networks that you are supposed to route to. How do you route it? We're not telling it. It's going to learn on its own. Okay. So all we're saying is these are the network addresses that you're supposed to route to later on. Okay. That's all. So let's go ahead and close this. So what's good about this? I did not have to specify the next hop. Number one, that makes it easy for me. Number two, we're going to take a look at use case where it's essential that we don't specify the next hop and let the router figure it out on its own. Anyway, let's go ahead and do this router one over here, rip, and do the same thing. So 192.168.1.0, 2.0, 3.0. So essentially we're adding all the routes that are going to be needed. So 10.0.0.0, 11.0.0.0. So not 111, 11. That's it. Okay, let's go ahead and close this. Do the same with router 2 as well. So over here, we're going to add 192.168.1.0, 2.0, and 3.0. So let's add these. Let's also add 10.0.0.0, and let's add 11.0.0.0. Okay. So all we've done is we've gone ahead and specified all the possible networks that we might need to communicate with. Okay. So fast forward, just out of habit, it's not really necessary here. Now let's go ahead and try to do some ping from this guy over here to this guy over here. So let's go to our simulation mode over here. So desktop command prompt, and let's say ping 192.168.3.101. Okay, so that's the guy, right? Yep. So let's go ahead and start this. So first we need the ARP. So let's do this really quickly. So when the ICMP packet gets here, you see that routing table finds a routing entry to the destination IP address, right? So why do we have that? This time we know that 192.168.3.101 is going to work. Why? Because the routing information protocol is going to automatically do this for us. Okay, so we did not have to specify where the path is or where the next hop is. All we specified was where the networks are, what the networks are. Okay, so it goes over here and automatically goes over there. How is that possible? It's possible because the routers communicate with each other and figure out how this thing is going to work. Okay, right. So let's go ahead and let this run, right? So that it can work. And let's go over here to this guy over here, Control C, because it's going to time out the first time because of all the ARPs. Let's go ahead and run this, and as easy as that, we're done. Okay, so we can ping everybody from everybody now. So 2.101 the first time might time out because of the ARP, but after that it should start working. Okay, so it took us like 2 minutes to set this whole thing up. Okay, with static routing we had to create this whole thing ourselves. Now let's go ahead and take a look at another use case which we started with, that we can also have a wire going from over here to here. So router 0 can be connected directly to router 2 as well. That's perfectly legal. In fact, that's very common to have multiple routes on a network. And why is going to be clear in just a minute. Okay, so let's go ahead over here. So let's connect serial 010 with this guy over here. Okay, and let's go ahead and obviously we need to configure these. So let's move this out a little bit over here so that it's slightly cleaner, right? So that we can see the wires. So this was 10.0.0.2. Over here, we're going to call this 12.0.0.2 with the mask, bring it on. Go ahead and close this, add a node, 12.0.0.0.0.2. So bring this over here, this guy over here, 12.0.0.2, 0.3, mask, on, close, fast forward. Okay, now let's go ahead and try to do this again. Okay, so a couple of fast forwards. go over here, enter the simulation mode, command prompt, and let's do the same thing again. Okay, so we are trying to go to 192.168.3.101. So if you hit enter, now this is going to go out and the packet goes out, and let's see which path it takes. It goes over here, okay, and from here it goes over there, and then it goes to the thing. So it's the same route that we had earlier on. Okay, now let's try to send this back. On its way back, it's coming as well over here. Okay, so it's taking the route which seems longer to us. Okay, so there is a lot of detail about how the routing protocol works. We may get to this later on in the theory, but for now you will see that this is the route it is taking. Okay, so it always goes through that route. But what happens if, so let's go ahead and run this to real time so that it finishes. So all the things are working fine. So let's go ahead and just make sure that it's working. Okay, now if you go over here and let's say for some reason this wire over here disappeared, I mean it was cut or there was some problem on this route, some network administrator misconfigured it, whatever, but this thing happens to disappear. So let's go ahead and delete this. Okay, so the only thing that has happened is that this wire has gone away. Okay, let's see what happens with our network as a whole. Okay, let's try to ping this again. The packet goes out, goes there, and it's rejected. Okay, fine. Then what? It's going to keep happening, and you'll see that it does not work at the moment. Okay, so let's go ahead and let this run, and you will see that you are getting a destination host unreachable. Okay, all right. The reason for this is even though we have added this wire over here, we have not told this router that this wire actually exists. Okay, so let's go ahead and bring that wire back. So make sure that you understand the problem. As far as this routing information protocol on this router is concerned, this 12.0.0.2 does not exist. Why? Because in this RIP we don't have it here. Okay, so let's go ahead and bring the wire back. Let's connect this to, this guy over here. So serial 001 and this guy over here. Okay, so the wire is here. Let's make sure the ping is now working. So we go over here, go to the ping, destination host unreachable. It gets it one time, but then it starts working. Okay, takes a little bit of time to for things to settle down. Okay, so it's working now. Now let's go over here and go to RIP and add. So all we're doing is 12.0.0.0. We're adding this to all three routing information protocol informations. Okay, so over here, similarly over here, and similarly over here. So this is a one-time deal. Okay, we do it once. So this is done now. Now let's go ahead to our simulation mode and try to do the ping again. So let's see what happens. You go out, and this thing now goes directly to this, because the routing information protocol has figured out that this is also a router, it exists, and it's going over here. Okay, so it has skipped this path. Why? Because now it knows that this network 12.0.0.2 exists, and therefore it knows that if I go over here, I'll get there directly. Remember that it's not important or it's not necessary that you always take the path which looks shortest to you. It's very possible that this wire is a slow wire and it takes a long time to reach here, and this might be a very fast router and a very fast wire connectivity over here. So this path actually might be a better route. That's not our concern here. Our concern is right now in this lab that there are multiple routes available. So right now it's taking this path. Okay, so we are going over here and this thing is working perfectly fine. So it's going through this route. Okay, so let's bring back our use case. What if this connectivity disappears? Okay, so let's go back to real time and let's go over here and make sure that the ping is working. It's working. What happens if this wire for some reason goes away? Okay, so this is the path that we're taking right now. If this wire goes away, you will see that it doesn't really affect us. How? You go to this and you go to the simulation mode and hit enter. So the first time it goes there, it goes automatically over here. Now, if we had specified this using a static next hop, then we would have had to say 12.0.0.3, which is this guy over here, and it would have tried to go there, but the wire did not exist, or the wire was broken, or whatever, so our packet would not have gone anywhere. That's the problem with static routing. You give it a static route. If that static route is not available, then the packet doesn't go. In a dynamic route, if there are multiple routes available and one route does not work, then the router is automatically going to route it through another path, and then it's going to work. Okay, so it happens, and as you will see, we are getting the thing working perfectly fine. Okay, so this situation over here shows you that you can have multiple paths over here. So imagine that you have 4 or 5 routers over here. They can be connected to each other in any sort of combination. So you have to make sure that you have the whole thing working in a sense that if one wire goes down, you have an alternate route available. So for all the major routes, you're going to have multiple paths. Okay, so this is dynamic routing. Routing Information Protocol, or RIP, that you see over here. So it's called RIP generally, Routing Information Protocol. It's one algorithm. There are also other algorithms available which do something similar, but they're much more intelligent. So what's the difference between a routing information protocol and there is another OSPF, open open shortest path first, OSPF, or something like that. I don't remember right now the abbreviation, but the point is the multiple algorithms are there. You can use different algorithms, and modern routers support different algorithms, and different algorithms serve different purposes, and they are useful in different scenarios. For now, all you have to understand is, for a dynamic routing algorithm, you have to specify very little, and one thing that you definitely don't have to specify is the next hop. So let's bring our wire back in over here, and then we can stop.